Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. This is part 3 of the Lithium Mine to Battery Line series. We'll be taking a close look at what Tesla referred to as cell design. Tesla advised that cell design would result in a 16% increase in range and 14% decrease in cost. Today we're going to look at how Tesla may have arrived at those numbers. Before we begin, a special thanks to Bradford Ferguson of Halter Ferguson Financial and the Patreon supporters listed in the credits. It's the support on Patreon that keeps me grinding away on niche topics. I'd also like to thank @Bimmer3D and @ByWhatMeasure on Twitter for providing me with excellent 3D object files to work with. Bimmer3D is selling a high-quality model of the 4680 cell on Etsy, and I'll link his details in the description. Finally, thank you to Peter Moraine of Glacier Design for rendering the animations from those 3D object files. You can also find Peter's details in the description. Back to cell design. We'll work through the cell design portion of the Battery Day presentation slide by slide, starting with cell diameter. This graph tells us that a larger cell diameter results in a larger cost reduction up to a point, and then there are diminishing returns. I have some speculation here. In the last video, I advised that my research for the original Battery Day series pointed to a 5 times increase in battery line speed due to the faster electrode output of the Maxwell dry battery electrode lines. When I discovered this, I thought it may be more than coincidental that there were rumors of a battery cell with a 5 times volume increase. My thinking was that if the 5 times volume increase were true, it would mean that a battery cell line that's producing electrode material 5 times faster would be putting out the same number of cells, and the line could move at the same speed. In other words, the battery cell could reduce bottlenecking throughout the rest of the line, and Tesla could use more battery equipment that's off the shelf because it wouldn't need to move any faster. It would just be dealing with larger cells. As I said earlier, this is speculation. I'm not sure exactly why there are diminishing returns on the cost reduction curve in this graph. However, I find it more than coincidental that the point of diminishing returns is at about 7 times volume increase, which would correlate to the 7 times speed increase of Tesla's dry battery electrode manufacturing line. If the cell volume is at a greater multiple than the potential line speed increase from the dry battery electrode line, it may provide little further production cost benefits. What about the yellow line representing vehicle range? It shows that by increasing the dimensions of their battery cell from 21 by 70 to 46 by 80 millimeters, Tesla was able to capture a 7% increase in range. We'll explore what Tesla means by range in a moment and how that equates to energy density. 7% is right in line with what I predicted. I estimated that a larger cell size of 40 millimeters by 70 millimeters would result in a 5% energy density increase from Tesla's current 21 by 70 cell design. A 4070 cell has a volume roughly equivalent to a 37 by 80 millimeter cell. This graph illustrates that a 3780 cell would provide roughly a 5.5% range increase. It looks like I was right on the money with my 5% energy density improvement estimate. Why does a larger battery cell result in a higher energy density? This is a 2170 battery cell compared to a 4680 battery cell. The volume of each cell consists of all its internal layers, which contain the active energy storing material. The surface area of each cell consists of an outer layer, which is the thin metal can of the battery cell. If we increase the volume by moving to a 4680 format, it reduces the total weight of the thin protective cell can in comparison to the energy storing internal materials. The graph on screen illustrates how the surface area and volume are affected by incremental changes to diameter. The surface area represents the cell can, and the volume represents the internal layers which contain the energy storing material. As you can see, the surface area doesn't change much, but the volume changes significantly. This means with a larger battery cell, there's more energy storing material in comparison to the cell can, which is just packaging. This is what results in the 7% increase in range for Tesla's 4680 cell. We also notice that the yellow range line also suffers from diminishing returns, and even starts to bend downwards past the 51mm diameter mark. I have two guesses as to why this would be. First, as the size of a battery cell increases, the cell can becomes a smaller proportion of the total cell weight, so there are fewer gains to be extracted by increasing the volume. Second, as the cell can gets to a certain size, it might need a thicker cell can to maintain rigidity. I imagine that a battery cell could only be made so large with such thin material. It was also suggested to me by a battery researcher that a thicker cell can might be required to get the right heat dissipation characteristics for a battery cell with a greater volume. There may be other reasons for the slope of the range line, but these were the first two possible reasons that came to mind for me. Note, I've excluded any reasons related to packing density because it's been debunked both in my BFC video and by Now You Know. This was probably the second most misunderstood slide at Battery Day. The graph shows supercharger time increase on the y-axis and cell outer diameter on the x-axis. There are two lines, a dashed line for the charge time increase using a conventional tab design, and a solid line representing charge time increase for Tesla's tabless design. What the dashed line for the conventional tab design is telling us is that charging time increases rapidly with cell diameter. A larger cell diameter results in more heat generation, and also makes it more difficult to extract heat from the battery cell. Heat is one of the limiting factors for battery charge rates. That is, the limiting factor for charge rate varies with context, but heat is what Tesla focused on in the Battery Day presentation, so that's what we'll focus on here. As a battery charges, it heats up. As it heats up, the resistance of the battery cell increases. That increased resistance also results in further heat generation, and the process becomes self-reinforcing. Heat goes exponential, and charging time goes with it. The solid line for the Tabless Electrode is telling us that charging speed only slows down slightly with increasing cell diameter. As Drew and Elon explained on stage, the way the Tabless Electrode does this is by reducing heat generation because there's a shorter electron path. That means there are fewer things for the electron to bump into on the way out of the cell. This means less resistance, which is like electrical friction. Overall, the graph is telling us that the Tabless Electrode allows Tesla to use a larger battery cell without negative side effects. The purpose of the larger battery cell is to reduce manufacturing cost. Tesla reinforced this by showing this image, which shows three key benefits of the Tabless Electrode. The first two, simpler manufacturing and fewer parts, directly result in cost reductions. The third, a 5 times reduction in electrical path, allows Tesla to expand the battery cell without a negative impact on charge rate. This again supports reduced costs by enabling larger battery cells. As I've said in the past, larger cells means fewer cell cans, fewer welds, fewer electrolyte fills, and so on from about 4,000 of each down to around 800 of each. I'm not saying that the Tabless Electrode wouldn't support higher charge and discharge rates. The massive chunk of highly thermally conductive aluminum and copper on each end of the battery cell provides a thermal superhighway through the core of the battery cell. This should support higher power density and better thermal management, which may support higher charge and discharge rates. I'm repeatedly using the word support for a reason. Power density is in large part determined by the chemistry and the internal structure of a battery. For example, in the last video I advised that Maxwell DBE allows for lower resistance. However, there was actually a better way to phrase that. DBE results in a chemistry that allows ions greater access to the active materials. That greater access increases the rates at which electrochemical reactions can take place, which means faster charge and discharge rates. The adjusted graph shown on screen is what it would look like if the benefits of DBE were geared towards power density. I'm not saying this is what Tesla's done. Rather, it's to illustrate one possible avenue to increase charging speed and to show what that would look like on this chart. What I've shown here is a 20% reduction in charging time. This may have been the most misunderstood slide from Battery Day. This image shows that Tesla increased the energy of the 4680 cell by 5 times and power by 6 times. Notice that they said power and energy rather than power density and energy density. If we take into account the 5.48 times increase in volume compared to the 2170 cell, this is saying that the battery has 0.9 times the volumetric energy density and 1.1 times the power density. Starting with the 1.1 times power density, this could be due to the Tabless Electrode, or it could simply be a side effect of a larger battery cell. As stated in the BFC video, larger cells tend to provide higher power densities. Either way, the 1.1 times increase is negligible. My view is that it gives us a minimum expectation about how much charging speed can be improved with the 4680 cell. The Tabless Electrode and larger form factor both fall under the general heading of cell design, and any chemistry improvements wouldn't have been factored in here. As Drew Baglino said in the Q3 earnings call, electrode design and anode material choice more directly determine the maximum charge rate. Charge rates will be discussed further in the Tesla Silicon video. Why would the battery cell have 0.9 times the energy density? There could be half a dozen different reasons for this, including rounding down from the 5.48 times energy density improvement resulting from the 5.48 times volume increase to provide an even number. If there is a technical reason, my best guess is that the internal, usable volume of the cell was increased by less than 548%. This could be because the hollow core of the cell is larger than a typical battery cell. This additional empty space would have a noticeable negative impact on volumetric energy density, but would have very little impact on gravimetric energy density. I do know that Maxwell's DBE technology wasn't responding well to being tightly rolled. If that problem wasn't solved, then we'd see a larger hollow core like we see here. This would result in a reduction in volumetric energy density while seeing an increase in range. The increased size of the hollow core could also be to allow for extra expansion of a high-loaded silicon anode. However, I'm assuming they deal with this by increasing the porosity of the anode instead. There are many more things this could be, such as the increased amount of dead weight due to the continuous tab of the awkwardly named Tabless Electrode. Ultimately, we know that with all the changes covered at Battery Day, Tesla drastically improved energy density. So I wouldn't put any stock in the 5 times number. Finally, the 16% range improvement is where things get really interesting for me. As we said earlier, Tesla was able to capture a 7% range increase from the larger form factor. Where did the other 9% come from? First, range doesn't equal energy density. We need to find a way to convert range to specific energy. Specific energy is how much energy is stored in a given weight of material. If you have 2 vehicles that store the same amount of energy, but one weighs significantly less due to higher specific energy, the vehicle gets a range bonus because it's lugging around less weight. However, the effect of that range bonus would depend on the aerodynamics of the vehicle, the tires, the vehicle speed, the road surface, the vehicle weight, and more. In order to pinpoint a conversion factor for range to specific energy, I ran multiple calculations using 3 broad approaches. Those 3 broad approaches were a physics-based approach, comparing different versions of Tesla's current vehicles, and using Tesla's own Battery Day slides. Most of my calculations ended up with 5 to 20% of the range increase being due to the weight reduction. In other words, for each 1% increase in range, 0.8 to 0.95 of that range increase was due to specific energy, and the remainder was due to a decrease in weight. I decided to split the difference, meaning that I chose 0.875 as my range to specific energy multiplier. Let's look at an example. With a multiplier of 0.875 applied to 16% total range increase due to cell design and 7% range increase from a larger cell diameter, it results in a 14% increase in specific energy due to cell design, with 6% of that coming from the larger cell. This leaves an 8% improvement in specific energy that's unaccounted for. I see two design choices that could easily bridge that 8% gap. In the last video on Maxwell DBE, I stated that Tesla could increase specific energy by increasing the ratio of active to inactive materials. That is, they could reduce the amount of binder and conductive carbon or increase the thickness of the cathode. Based on the options I laid out, I settled on increasing the thickness of the cathode. I suggested that increasing the cathode thickness could easily increase the specific energy of Tesla's cells by around 5%. There's nothing to indicate that this is the path that Tesla has chosen other than the 8% gap discussed above. However, a thicker cathode is something the battery industry is pushing hard on because it amounts to a free energy density increase if power density can be maintained. Maxwell DBE does just that. The second design choice appears to have been already made. In my Tabless Electrode video, I said that the Tabless Electrode would reduce resistance. I suggested that reduction in resistance would reduce the energy wasted as heat and that it would be equivalent to a big screen TV in terms of energy and heat. I calculated that this could be up to a 10% reduction in heat generation and therefore energy loss. I didn't know how that would play out in reality, and I'd actually forgotten about it. I also didn't know if it could be technically classified as an increase in energy density, because it was really a boost in efficiency. However, Tesla eliminated the wall between energy density and efficiency and lumped those two together under the banner of range. There are two things that make me more confident that the resistance reduction provided by the Tabless Electrode would provide real-world benefits. First, the clear 8% gap in Tesla's presentation indicates there are other synergies going on with their cell design. Second, last week I was watching a video by EEV Blog, where he calculated that the energy savings of the Tabless Electrode might be around 5%. This confirmed to me that my calculations were in the right ballpark. A 5% specific energy increase due to a thicker cathode and a 5% energy efficiency improvement tally up to 10%. This easily closes the 8% gap in Tesla's presentation. The numbers are so close here that either the thicker cathode or the energy efficiency improvement could alone close the 8% gap. If I'm correct here, then both of these improvements would have been primarily driven by the goal of reducing cost, and the specific energy increase would have been a secondary goal. This brings us back around to the most important part of the Battery Day presentation, and a major theme of this series reviewing Battery Day. Tesla is ruthlessly and single-mindedly focused on cost. With a 54% increase to range available to future versions of the Model 3 and Model Y, the vehicles could hit over 500 miles of range if Tesla chose to do so. In other words, in terms of range for vehicles, energy density is now a solved problem. However, accelerating the world's transition to sustainable energy is not a solved problem. Solving that problem is a game of cost reduction, manufacturing volume, and manufacturing efficiency, which are all tied at the hip. For me, this means the cell design was one key piece of solving the cost and manufacturing problem. I'd put it as the second most important of the 5 projects unveiled at Battery Day. The Maxwell DBE line is the most important project and sits at the front of the battery line, accelerating electrode production by a factor of 7 times. A 7 times speed increase would be far too fast for standard manufacturing equipment to keep up if the cells were the 2170 size. The 4680 cell design allows for 5.5 times the line output of a 2170 battery cell line while allowing the line to run at the same speed. Closing the gap from that 5.5 rate to match the 7 times rate of the DBE electrode production is totally doable by Tesla, and I imagine the Tabless Electrode played a big part in closing that gap. As the Battery Day presentation made clear, continuous motion is key. Battery tabs create points in the manufacturing process where there are stops and starts. For example, tab welding. In previous videos, I've stated that eliminating tab welding could alone save 5% to the cell cost. In summary, there was a lot of tech buried behind the simple graphs that Tesla showed us at Battery Day. Even what I shared today was an oversimplification and involves some speculation. Tesla opened the door just a crack at Battery Day to give us a glimpse of what they're working on. What else do they have in their skunk works? Whatever it is, you can be assured that it's focused on reducing costs and accelerating manufacturing speed to transition the world to sustainable energy. The new cell design increases range by 16% and reduces cost by 14%. Given that battery energy density usually only increases by 3 to 5% per year, we received a 3 to 5 year leap in technology with the new cell design alone. In the next video, we'll take a closer look at the cell factory portion of the Battery Day presentation. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to Rick Thor and James Aspinwall for your generous support of the channel, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.